Atong sige, magsugod na ta no. So good evening. We will be uh, um, discussing sa ato ang bag-ong topic, which is the scope of our midterm exam no, which is the DAMP single degree of freedom karon. So this lecture most likely 1 hour kapin lang. It's not actually long, no. It's actually short because we already covered a lot sa ato ang um, sub chapter 2 kani daghan kita na cover na. So chapter 3 is just a little bit more, gamay lang kay ang addition nato no of our learning. So ang second reason why na short lang sa takay, sige gyapon while I'm feeling unwell pagyapon, so sige gyapon ko ubo, gikan ako hilantan sa tungod sa panahon, so I'll try to make this short no. So the notes is already it was already distributed no as a PDF no earlier no, so you can refer to that. So atong na i-discuss karon is our new topic no, chapter 3. Okay, so I'm pretty sure ang uban wala pa siguro naghimo sa mga problem sets 1 to 6 no, and I have confirmed that yesterday gabi gabi no, wala pa gid nagsugod sa problem sets. So again no, reminder lang, this was given like last week pa man siguro to actually give to for you guys to solve it no. Pero sige, ako na extend ang deadline up until Wednesday. Then I will not be opening the canvas yet because I have learned that people did not actually solve it pa. Sige, so I will be extending it up until Wednesday. Pero ang nasa problem sets for this chapter 3, and then this is also due on Saturday next week. And your problem sets of the chapter 3 is actually related sa imong problem sets sa chapter 2. I made it that way para ma-focus kit mag-solve. Okay? So, later ako ni-discuss, no? So, we'll be discussing the analysis of the DAMP single degree of freedom system today. So, basically, what we have learned last time, no, is this equation, right? This is our differential equation that we have learned last time, no? But what we did is ang atong equation is kanira involved, no? So we did not involve the damping constant, no, or the damping term, no. So karon kay will be including the damping system no, or the damping term of our differential equation. So if we're going to solve this differential equation no, to actually analyze a damped single degree of freedom system no, so ang the image or the what you call that, the problem is looks something like this no. Inani siya, same gyapon no. So this is your mass M, and then kanisha is your x na displacement, this is your k, and then this is your c. So same gyapon ato ang derivation. So what we're going to solve now is actually how to solve our differential equation na with a damping no. So to solve for the differential equation with a damping constant, we'll still be using the trial solution no, x is equals to ERT kani siya. So you get the first derivative x prime and the second derivative x double prime no, and you substitute those answers into the equation, into this equation no, and you will end up sa kanina equation, so is equals to 0. Okay, so what will happen is you have turned your differential equation no, into an auxiliary equation, an algebraic equation that you can solve using the quadratic formula. No? Everybody knows the quadratic formula, so we'll be using the quadratic formula to actually solve for our our auxiliary na equation, which is we want to get the R1 and R2, no? Okay, since you have a positive and negative na sign here. So, going back, no? So, ang A na to is the mass, ang B is the damping constant, and C is the constant of the stiffness. Okay? So, rewriting sa atong equation, kanisa na equation, no? This is our quadratic formula. We just literally substitute it. Ato rewrite in this form, no? In this form lang because for later discussion, atong gipagawas ang kaning C na term, no? Kani siya C, and then na-rewrite ta, no? Ato ang kaning 2m atong gipasulod sa ato ang square root, it became c squared over 4m minus k over m, no? So, sa kanina particular problem, our solution is actually sa case 1, no? Case 1 of our differential equation, which is distinct ang atong solution, no? Distinct atong solution. So therefore, if distinct gani atong solution, your solution now is therefore C1 e to the R1t and C2 e to the R2t. No? This one was already learned from our differential equation na course. No, of course, ang C1 and C2 is our constants of integration. Okay? So now, since ang problem karon kay we want to solve for C1 and C2, no? So usually we have three na pamaagi kani siya. So naatay tawag og kanang critically damped, overdamped, and underdamped, no? So ang kana siya is actually depende na siya sa sulod sa ato ang sa sulod sa atong square root kani siya. So if ang c squared, no, is equals to 4mk, or in our notes is if kanisha is equal to k over m, this is what you call a critically damped na system. It is not, it's in between overdamping and underdamping, no? So usually mo na tong gamiton to solve our single degree of freedom. This is what this is our basis, no, sa atong critically damped na system, no? So usually sa structural engineering na problems, our solution or our structures is usually underdamped, no? Underdamped atong mga problems are our structures. A rare case rajud ang overdamped, no? Very rare case. So sa atong discussion, I will be discussing that critically damped and the underdamped, or I will be disregarding the overdamped na situation, no? Okay? So, if we are going to solve for our critically damped na problem, no? Critically damped na problem, what will happen now is we will be replacing our C is equals to C subscript CR, so which is the critical damping. So shortcut ni siya na term na critical damping. So to solve for the critical damping, we will be getting kanina equation, no, which is the nasa sulod sa ato ang radical expression. So going back here, no, kanina na radical expression mo na atong gi-equate with each other, and then to solve for C, no, which is atong gi-substitute, nahimo siya C subscript CR, or critical damping, no? So we have this equation, okay? So we are interested in solving for C sub CR, the critical damping. So what we do is ang kanina term balin sa right side, no? And then kanina na term i-multiply, cross multiply. What you get is kani na answer, or this one. Okay? So ang critical damping di ay na equation, no? The equation is actually twice times the square root of k times m, no? So where CR is the critical damping value, no? And then since the natural frequency or the angular frequency of the damped system, omega, is square root of K over M, ang critical damping SAD, no, has also similar SAD expression. So you can write the critical damping in terms of K and M, or you can write it either K and omega, M and omega, or K and omega. So mato atong tulo ka solutions, no? Or sorry, tulo ka equation. If given ang K and M, you can solve for the critical damping. If you have solved for the omega, which is what we usually solve for, the angular frequency, no? You can solve for the critical damping from using this value, or you can solve for the critical damping if you are given the K, your stiffness, and the omega, no, or the angular frequency. So if in the critically damped system, our roots, which is ang R1 and R2, is actually equal. So kaya naman kay equal man siya, no? So meaning anak niya ato ang solution, atong differential equation, if we go back here, kani siya, if it is equal, kani siya mo-cancel out, right? Mo-cancel out siya. So that leads to kani siya. So, kung ma-cancel out ni siya, mabiling gyapon ang R1 and plus and minus sign, no, which is 0. So, ang R1 and R2 is actually equal to negative C over 2M. If we remember our differential equation, no, if we have a repeated roots, our equation or solution is therefore kani siya, no? So we have this one as our what is part of the solution. So mahitaboan ni karon kay ang C1 times e to the R1, no? E to the R, and then ang C2, no? You just multiply a independent variable t, and then you repeat the e to the negative CR over 2MT. Okay, this is the solution kung equal, no? Equal. Critically damped na siya. So, if critically damped, which is a very, very rare case, no? This is our solution. Mahitabo na siya, pero rare kaya na siya mahitabo. So, our interest in this study sa structures, no? Structure engineering, is actually the underdamped single degree freedom. So, unsa may meaning sa underdamped, no? Sa underdamped is, if we go back here, ang underdamped is actually kung ang ato ang term kani siya na term is significantly less than kanina term. Mahitabo anak niya ma-negative ato ang sulod sa ato radical symbol or the square root symbol. So that is why we already in the notes naka-provide na ang letter I, no, because it is already indicated as a imaginary na ang iyang solution. Okay? So if that is the case, then we will be using, no, the technique sa atong differential equations katong solution e to the alpha t plus C1 cosine of beta t plus C2 sine of beta t, which is kani atong gamiton. So we have to identify what is the alpha and what is the beta, no? Pero it's very clear. Atong alpha is the is kani siya kanang wala nagtupad sa I, and then ang beta is everything na nakatupad sa I, no? So this is our solution. So the problem karon is how do we solve for C1 and C2, no? And by the way, ang kani siya ang beta na term kani siya is very similar, no, to the natural frequency omega sa atong undamped na free vibration, but in our study sa damped or specifically underdamped free vibration, this term is actually called a damping frequency, no? Damping frequency of the system. Okay, so if magsulti ka natay damping frequency of the system, it is usually better or best, no, to introduce what you call a damping ratio. So ang damping ratio is just a ratio between your damping na constant, no? Ang C, damping constant divided by the critical damping. Moto nagtuon ta earlier section, we need to know how to solve our critical damping. Because in the field of structural engineering, usually our interest is the damping coefficient and unsa ang iyang ratio, no? Ratio between the damping and its critical damping. Okay? So, same gap no? So, if we introduce a damping ratio, no? And then the natural frequency or the angular frequency of the system is still square root of K over M, the damping frequency of the system can be similar, no? It can be similar in writing. So kung omega ni siya, omega capital D is the damping angular frequency, which is atong radical symbol ganiha, no? Square root of K over M over C over M2M squared. But ang kani siya, no? So if we're going to introduce a damping constant, what will happen now, a damping ratio, what will happen now is we can relate the damping of the system, no, sa damping system with the undamped system, which is your natural frequency or angular frequency times the square root of 1 minus epsilon squared. So ang kani epsilon is your damping na ratio. So what happened now is how we understand this equation is kani si omega t or kani si damping na frequency of the system is equals to your your natural frequency or your angular frequency of the free vibration system, no? Naka-free vibrate siya, which is what we have learned in chapter 2, and then nag-multiply ra siya some sort of a factor, and that factor includes your damping ratio. That is why we introduce the damping ratio to this equation. It's because we only need to solve our system, even though it is damped, atong gisolve siya, we treat it as an undamped system, no? And then we just multiply it by a certain factor, which is 1 minus damping ratio squared, and then you just get the square root. So, if mo na ang case, then our solution now is therefore kanisiya, no? So, going back to our differential equation, we learned that kanisya is the decaying factor, and then this one is our sinusoidal na factor. Okay? So nga naman decaying because if you observe this equation kanisi under sa E, no, the Euler's number, we have a negative sign. Ang kanisi a negative sign indicates that your system is decaying, no? Ang vibration niya, ang iyang vibration is decaying, no? So moto siya nag-multiply siya sa kanina factor, which is our sinusoidal na graph, no? Okay? So now, if we have this equation, no, what we need to know now is unsa ang pagkuha ang constants of integration, no? Pero sa iyo ng gyapon, no, the same strategy applies that we did sa chapter 2, no? We will just introduce the initial boundary conditions, which is at rest, no? At the beginning of the system, we have what you call your initial displacement, and at the beginning of the system, we have also what you call the initial velocity, no? If you did the math, if we do the math, or if you did the math, no, or will do the math, you can solve for C1 and C2, no? Is this one. So kung substitute ta to solve for C1, actually, no, ang kanisham, ang iyang answer is your initial condition due to displacement, and then your initial, when you substitute the initial condition due to the velocity, you get this constant, no, which is what we did, no? Similar kay siya sa ato ang earlier discussion kato chapter 2 na discussion. This is very very similar. The only difference is na kay epsilon, no, which is the damping ratio, and we also have the omega d, no, which is the damped angular frequency, no? So if we have all of those, then if we can also say that we have our period, no? So the damping period, no, dili undamp, the damping period is actually 2 pi over omega d, which is similar gyapon sa atong previous na lecture, which is equals to kani, no, 2 pi over omega times the damping constant, no? So what happens is, if mag-plot ta ano niya, if you plot this solution, it will look something like this, no? So our system now, kanina solution or kanina system, no? This is what we have, a free vibration response of a damping system. Observe that our kanisha, our what you call that, no? Our vibration, no, is still a sinusoidal wave, no? And then it is dependent upon your period, no? Period of vibration. And then observe sad kay naghina-hina siya decay, no? Mahimo siya og zero over time. So the difference between chapter 2 and chapter 3 is actually this one, this constant, no? Sa katong atong gi-multiply sa ato ang equation, kani siya na equation. Okay? So so if you want to solve for C, no? Because kanito siya, if you want to solve for C, you just bring this out. You just bring that out. So I did it for you already. So mali siya ang atong C, no? So this dotted dash line na red marker that I've drawn here, no, is actually C times epsilon, times E, no? Times E, the natural logarithm or the Euler's number to the power of negative epsilon, which is our damping ratio, times the omega, no, which is our angular frequency, and t, which is our variable time. Okay? So take note that moto akong gibutang note diri, ang damping coefficient for real structures is much less than the critical damping coefficient, no, which is usually ranges from between 2 to 10% sa mga underdamped. So if you go beyond damping, go beyond 10%, it is actually overdamped the system. Okay? So to prove that point, no, ato gi-substitute kani mo gamit ka kaning 10%, no? So if we will try our critical damping, our damping ratio, we will set this as 10%, and then we will try to solve for the damped natural frequency or the damped angular frequency. If we do the math, no, kani siya 1 minus 0.10 squared, no, this one is just a factor that is equals to 0.995 omega. So meaning ana niya, no, ang kanina answer is actually close to what we have solved in chapter 2. It is very close to the undamped natural frequency of our system. No, that is why we learned in chapter 2 how to solve a free vibration lang, an undamped free vibration, a single degree of freedom, because we can actually estimate, no, the natural frequency of the structure based on the free vibration. So moto akong ginote na thus in practice, the natural frequency of the damped system can be taken equal to the damped natural frequency. Okay, so moto siya, this is what we need to learn right now, no? The only difference karon from what you have learned previously is this term. Kanara gid siya, no? And then everything else nag-multiply rata sa atong undamped na free vibration. So the difference in terms of sa graph is your vibration now is decaying. Nag-decay siya tungod sa kanina na term, no? Kanina term. So moto siya. Okay? So heavy siya sa math, but sige lang, no? I have 3 examples to explain later and how to apply our knowledge, no, sa damped na free vibration response. Okay, so before I would continue sa kani very important na topic, na ba mo'y questions and clarifications before we continue? And then, I don't know kung magtanaw ko sa chat, no? How do I tanaw sa chat? Yeah, in call messages. There we go. Okay. So, can I move this to the other screen? Move to display. There we go. So na ba? Or wala ra? Okay ra? Okay. So, no? So, sige. Maybe, as usual, loading pa, no? Sige lang. So, don't worry, no too much. If, again, no, the point here is if we try to solve it, if you try to solve the differential equation, no, mo balik it ka derive everything, you will get more insights. Kay kung ako, if I explain it karon, that is how I interpreted when during sa ako ang pag-solve sa akong differential equation, no? So I would highly advise na just try to solve it. So if we're going to go, no, sa kaning chapter 3.3, which is the last topic, no, short ra gid na siya na chapter. So ang kani siya na logarithmic decrement is a method, no, to determine experimentally the damping coefficient of the system, no. So ang what we do, no, which is hopefully naadiri katong mga akong mga thesis karon, no, akong thesis group, this is what we need, no. So if we are going to do an experiment to our structure, we need to know what is the damping coefficient. And to determine the damping coefficient, what we need to do is first to initiate free vibration, no? So how do we initiate free vibration? Kung ako na i-drawing diri, kung this is our very simple na frame, ay na lang kani. Ako na ihimuon masayon pa the famous lollipop model, no? No? If na ko a lollipop model, which is your structure, what happened? There. If this is my lollipop model and this is my mass, no? What we do, no, is we pull it first, no? We pull it, we set our initial condition, like for example, let's say 25 mm, no? So kani siya arbitrary na rin siya, and then after pulling it, we remove the load. What will happen is it will oscillate, no? So more siya moana siya. So more siya ana siya, and then moana siya, and then it will slowly die down, no? So mo na tong buhaton, and then we have to record the period, no? And very easy raman ang to record the period because we just need to time it. Okay? So first is we initiate free vibration and then obtain the record of the auxiliary motion, no? Okay? So which is, if we want to record the auxiliary motion, usually we record its displacement and its displacement at its acceleration, if we can, the velocity, no? Pero what we did is we know from our research, usually naatay sensors that can record acceleration data. So sensor acceleration data, but if you want to record the displacement, then I would suggest, no, if we have this structure, kanisha, the structure, you provide a setup na naki-structure, and then sa likod sa structure, no, pagbutang ka grids. So I would erase ani. Ang kanisi grids, maghimo ta grid line ani niya. So kani siya grid line, more siya ruler. So if I'm going to draw my lollipop model there is a center, like so, no? So kani ang 0, then maybe kani siya 1, 2, 3, and so on and so forth. Then kani siya -1, -2, -3. So if you want to measure free vibration, using displacement, you can use this setup. No? So, pwede kaya na siya. And then, what you do now is, since nindot na magkaya atong camera, especially kaning more than iPad or iPhone, no, or Android na medyo mahalon gamay, like mga 20,000 plus ang iPhone, 20,000 plus na Android, na makitawag naman naman tay feature what you call the slow motion na camera or na video, right? So uh, we record this experiment katong naka-oscillate siya back and forth in slow motion para makadetermine ta pila gyud iya maximum na displacement, no? So moto siya ang usa ka experimental setup that we can do, no? The other way is we have the same experimental setup like this one, like a free vibration, but we will be attaching a acceleration na sensor. So if maglihok ang ato ang lollipop model or atong structure, the sensor, the accelerometer, which is a sensor, can detect or can obtain a record, no? Maka-obtain siya record very accurately, no? Kay kumuliyok-liyok ang lollipop, so muliyok-liyok siya left and right, left and right, left and right. Ang kani sa accelerometer, at every second, no, more siya mo record siya to 100, I think 100 records per second, no, which is what you call your frequency of your record. So maka-determine kita pila gud iya acceleration at 100th of the second, which is we can also determine from that experiment, we can determine actually the damping constant, no? So to get the damping constant, so I have explained I have explained the experimental setup. So to get the damping constant, no, we want to record the decay, no, the decay. So the decay may be conveniently expressed by the logarithmic decrement, which is what we call the delta, which is defined as the natural logarithm of the ratio of two successive amplitudes U1 and U2, no, in the free vibration. Meaning anak niya, if we go back to this one, unsa may U1 and U2, the first two successive na reading na peaks, this two, no, is your ang distance ana niya is defined by one period, no, so one oscillation. So initially you record first peak and then we record again the second peak because we will be having a very hard time to record the smaller peaks kay dili naman siya ka detect sa accelerometer, no, or even sa atong mata ko bag slow motion mode ta, very 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 hard na siya. So theoretically speaking, our logarithmic decrement is equals to the natural logarithm of our two peaks, no, amplitudes U1 and U2. So if you want to verify how we did it mathematically, no, so mo na iyang pamaagi kani iyang derivation. So we will go back to our differential equation, no, and then we will just isolate a very simple na wave, which is a cosine na wave lang, no, to make this simpler in terms of our derivation, no. So we note that when the cosine factor is 1, no, so kung cosine 1 daw ni siya, the displacement is on points on the exponent of the curve x of t is equals to c e to the negative epsilon omega t, no. So meaning ana niya kung kani siya daw mahimo siya 1, right, ang kanina mabilin ang term, no. So however, these points are near but not equal to the positions of the maximum displacement, no. Near siya but not equal based on our kanang tao ani experiment, no. So ang actual points of our peaks, no, is actually slightly to the right of the maximum amplitude, no. So ang reason ana niya kay naman siya some sort of error in natural error yun sa atong system, no, once we record, which is it is 100% normal kay dili man ta ka perfect og recording yun on any kind of experiment, no. But for the most practical applications, no, this discrepancy is actually negligible, and we can treat that the amplitude on the curve and its displacement is to be equal. Okay? So if magtanong ta sa kanina graph, no? So kung maghimo ta sa experiment and then we release it and then nasa damping, no? We don't know the damping yet. Theoretically is na kay curve mo ana siya, and then it will slowly die down ana siya, and then mo stop na siya, right? So what we do is you measure the first peak and then the second peak. Okay? The second peak. So ang sa kanina curve, nagsugod ko sa 0, and then ang distance between niya is actually one period away, no? So mo to mahitabo sa kaning duha ka peak, no? So if diri ka nag-measure ang iyang maximum na amplitude, no, kani siya, so you measure from here to the first to the another na period, no? So mo na ay yung distance away, no, in terms of seconds. I-clear ba na ito istorya? So ang usa ka peak, this is the first peak, no, U1, and then the second peak is U2. Okay? So if mo na siya ang case, no, so we may write for two consecutive peaks, U1 at time 1 and U2 at time T, period D, no, the damping period, seconds later. So mo to siya. So mo to sa ang U1 and U2. So we have this mathematical equation based on our assumption na mo gid mahitabo, no, sa system. So if kani si U1 si U2 atong buhaton kay ato na i-divide niya. I-divide nato niya, so ako ibutang like ana siya, no, mag-divide ta, what will happen is kani siya na term and kani siya na term will cancel out, and what will remain is your kani siya na term, no, epsilon, omega, and your TD. So nawag tang ang kanina factor, no, kanina factor. What will remain is kanina siya na factor. You get the natural logarithm of these two because again, no, ang reasoning why nagkuha tag natural logarithm, it's because ang kanisya is within sa ato ang natural na Euler's number, no. We want to solve for our damping ratio. So we need to multiply natural logarithm for that to cancel out. Mo na nahitabo diri. So therefore, our natural logarithmic decrement is delta is equals to 2 pi epsilon divided by 1 minus epsilon squared because naman tayo omega here, no? Okay, and the period here, no? So na period atong gi-substitute, mao na siya. Pero if we remember that our structure is underdamped, no? And usually ang underdamped na maximum pagyud na niya na tawag ani kanang value of the damping ratio is 10% only, which is very small, no? Very small. So if that is the case, kanisha we can just treat is into as 1, no? It's because if this number is very small, no? Let's say for example 0.01%. So 1 minus kanina number is almost negligible, no? And then imo pagid kuhaon og square root, no? So if mo na ang case, we can actually estimate our logarithmic decrement by using this equation, no? So the logarithmic decrement delta is equals to 2 pi times your damping ratio. More atong baton, no? So which is easier to compute, no? So if we have the damping ratio based on our experiment, no? So mo na atong buhaton. Okay? But there are times, no, it's easier to compute our logarithmic decrement kung in terms of acceleration or peak acceleration, right? So related man ang displacement and acceleration. So ang relationship niya is the displacement or the acceleration is twice you have to integrate it 2 times to get your displacement. So, nasa direct na correlation. So kung na acceleration, mulihok ato ang displacement. Kung wala acceleration, meaning na niya, kung zero acceleration, wala siya velocity, meaning ang kato na area na walay acceleration is your maximum and minimum na displacement, no? So if you're going to do the math, no? If you're going to do the math, we need to get same gyapon na equation. That is why we use this equation, no? The simplified one, kay we have to get the first and second derivative of this one, of the equation. So task kani siya, no? And then, but you can just read this one, but ang important karon is, if you do the math, no, actually, ang logarithmic decrement is actually similar to the displacement, no? So, kani siya na equation in terms of acceleration na. And what we found out is, if we did the math, ang ratio between the acceleration and the ratio between the displacement is equal, no? You can actually solve for the damping ratio, no? The damping ratio by just getting the natural logarithm of your two peak acceleration, divide it by the omega and the period. So you can get the damping ratio. So sa atong experiment, if ma-experiment ta puhon, what we need to do is if we have acceleration data, then what we need to do now is actually just measure the maximum and minimum acceleration. Maximum meaning maximum positive, and minimum meaning minimum. So the smallest number in terms of negative value. And then you can actually solve for the critical damping. Not the critical damping, but the damping ratio, because ang epsilon again is the ratio, no? Balik ta. The epsilon is actually the ratio of your damping na coefficient divided by the critical ratio, critical damping, no? So mo man ang definition niya. Okay? And the critical damping, no? The critical damping can be solved mathematically. Kani man ang question mark. Okay? So mo to siya, no? So this is our how we measure damping. So ang summary ani niya na lecture is, you need to have a mastery sa atong previous lecture, ang chapter 2. That is why mas daghan kayo ang problem sets dito, kay ang module 3 or chapter 3 is just an addition to the previous lecture. Nag-add ra gyud tag damping ratio. More gyud atong gibuhat, no? So mo to sa ang lecture all about. And then now dagay na ta sa tulo ka examples. So these 3 examples is how to apply the ato ang mga knowledge in terms of damping, no? If na damping atong structure, which is, by the way, the real behavior of a structure. So before we move on, no, to our problem sets, no, not problem sets, ato example sets, na ba may question and clarification? So tanaw na to sa chat. So before we continue, wala ray questions and clarification. Sige. Sama na siya, no? So sige ko kaubo. Okay. So kung wala siya, then mag-continue ta. Oops. So we have 3 examples. Simple gani siya na examples. Dili kay siya kanang out of this world, no? So ang example number 1 sa chapter 3 is unsa to? It's like this, no? So natay a very simple na vibration na system, no? Wala siya figure because we don't need a figure for this one. The nakay system daw that consists of nasay weight, no, of 10 pounds, and we have a stiffness of your structure 20 pounds per inch, no? So it is already solved, no, or it is already given. So, pero ang natay viciously damping or viciously damped, no? That so that the ratio of two consecutive amplitudes is 1 and 0.85. Okay? So, very important. So, meaning ana niya, kung nagana tayo amplitudes, na measure ang amplitudes, no? We need to use the logarithmic decrement. So, determine the following, no? The first one is the the angular and natural frequency of the undamped system, no? So, meaning ana niya, free vibration siya na undamped. The second one is the logarithmic decrement. The third one is the damping ratio. The fourth one is the damping coefficient. So, lay ang ratio, lay sa ng coefficient. And then the last one is the damped natural frequency, the omega subscript T. No? So, karon kay, okay, we need to solve for the natural frequency or the angular frequency or both, no? So, again, no, from our previous lecture, omega is just square root of k over m, no? So, which is given ang k, given ang m, ang kanisya, there's no need to explain further because we already solved it, no, sa kani. Or, if you want to solve for the natural frequency, no, of the undamped system, katong na cycles per second, then we will be solving for natural frequency f, no, which is omega over 2 pi. This is the answer, no, 4.42 if we tuplok sa calculator. So, ang next question is, how do we get the logarithmic decrement? So, we have two amplitudes man, the 1 and the 0.5, no? So, what we do is the bigger one, divide it by the smaller one, get its natural logarithm, no? You get the answer. So, kanisha, this value, this logarithmic decrement na value, we will be using this value to solve for our damping ratio. So the damping ratio, again, no, kung ako isuwat balik, no, ln of u1 over u2 is equals to epsilon, epsilon, let me scroll back, no. So epsilon, there we go. Epsilon omega TD. Epsilon omega ED. There we go. So mo na ato ang tawag ani. Mo na atong formula. So we want to solve for this one. So what we need to do is epsilon is equals to ln of u1 over u2 divided by omega and TD. Okay? So this is what we do, no? So ang nahitabo man gid karon kay ang natural period, no? Natural period is 1 month. Right? So mo to nahitabo diri kanina equation, no? So epsilon is equals to your logarithmic decrement, no? Your logarithmic decrement divided by 2 pi then TD, no? Ang 2 pi is your omega earlier. Omega and then your period, no? So mo to nabili na lang kay 2 pi. So we substitute this equation, no? And then we get the answer for the damping ratio. So if we have the damping ratio ang epsilon, we can get now the damping coefficient, which is epsilon times your critical damping, no? Which is a critical damping, if you remember earlier, the critical damping CCR is equals to 2 times square root of km, no? This is the formula that we're going to use. So substituting using that formula and substituting it sa kani, and then taking note that this 386 is just a conversion factor because again ang 10 is pounds, no? Pounds ni siya, and the 20 is pound inch, but we have to convert our weight into mass. So weight to mass is in terms of pound slugs, no? Pound seconds squared per inches. You need to divide it by 386, and this is the answer, no? So Mo to siya, wala kay difference in terms of answer, no? Okay. So the natural frequency now is therefore kani siya of the damp system is W omega D is equals to omega okay. Kani siya is equals ani siya. Is equals to omega times the factor no na square root of 1 over epsilon squared, or is equals to 27.28, which is the damping what we have solved earlier, the damping ratio, the omega no, so natural frequency or the angular frequency times your damping damping coefficient no, so 1 minus epsilon squared, and you get this answer. So take note no, or take notice that kani siya si natural damping is very near sa atong natural frequency or angular frequency sa ato ang system. No? Doon lagi siya. It's because our damping is very small, no? Ang epsilon nato very small. Mo na reason. So that is why usually if we want to solve for our damping system, we can actually, there are times that we can actually use the free vibration no to solve for the period, for the natural frequency and stuff like that no? So mo to siya, very simple na tawag ani na example no. So before we move on to the second example, second to the last, dapat question and clarification. So mabalik na ko sa pika sa screen no. So dapat question and clarification before we move on. Wala pa of the moment. Okay. Anybody else? Okay. Pwede mo asa gikan ng 0.026 sa pag-solve sa damping coefficient. Asa gikan 0.026 no. So kani siya okay. The wrong kani siya the answer is actually 0.026. The wrong kog sakto. Kinarong kog copy no. Karong kog copy sa ako ang notes. So actually this answer here is should be 0.026. Wait. No. Not this one. No. Wrong. This one. 0.026 no. So let me get my calculator. Double check rin ako kung sakto ba akong i-compute. 0.163 divided by 2 divided by she time. Yeah. So, this answer should be 0.026. So, please record ka ng edit sa to notes. So, kani siya, wala siya units, no? Wala siya units. So, money siya dire. Okay. So, anything else? So, mag-correct ako after sa ako ang notes. Wala na yung other questions? Before then we can move on to the second example. So far, wala naman, no? So, what we can do now is we will move on sa itong example. Next example. Yeah. So, a little bit trickier na ang kanina second example. So, we have a platform of a weight 4,000 pounds is being supported by 4 equal columns that are clamped to the foundation as well as to the platform, no? So kung mag-imagine ka na niya, so naki-platform, no? Naki-upat ka column, 2, 3, 4, and then naki-foundation. So naka-clamp siya, so fix siya. Fix iyang behavior. So experimentally, it has been determined that the static force of F, no, is equals to 1,000 pounds is applied to the platform, and it produces a displacement of equals to 1/10 of an inch, no? It is estimated now that the damping of the structure is of order 5% of the critical damping, no? 5% ra sa atong critical damping. Okay? So, determine the following, no? So, first one is the undamped angular frequency, no? The absolute damping coefficient, the logarithmic decrement, and the last one is pila ka number of cycles now and the time required for the amplitude of motion to be reduced from an initial value of 0.1 inch to 0.01 inches, no? And I'll tell you why kani number 4 useful ni siya na problem later. So first, no, si undamped natural frequency or undamped angular frequency, same gyapon, no? So we go back to the theory of kanang elasticity, no? Force is equals to K times X, no? Oops. Force is equals to stiffness times the displacement. Displacement. Ano siya? Na siya. No? If you want to get the stiffness, well, we divide the force with its corresponding displacement. So, which is freely given sa tuang example, which is na kay 1,000 pound, no? Pound force divided by 0.1, which is this one, the displacement. Okay? So we can get now the stiffness coefficient. So if natay mass, natay stiffness, well, we can get now our angular frequency or the natural frequency, no? So the angular frequency is still, no, omega, kanisha, o this is omega is equals to square root of K over M, no? Or another version is K times gravity divided by omega. So, mato siya, no? So, the critical damping now, so naka-solve na to sa natural frequency or the angular frequency, which is the first requirement. The second requirement now is the critical damping. So, kani si critical damping is, para gyapon, no? Atong equation, 2 times square root of Km. So, nanatay K, which is 10,000, and nasa tay M, no? So kani siya again, ang 386 is just a conversion factor from pound force into slug, no? Slug in terms of inches. So you can get this answer. So if we have the critical damping, we need now to solve for absolute damping. Ang absolute damping is actually your damping na coefficient of your system, no? So which is C. So C is equals to epsilon times our critical damping, which is kanisha, no, times 0.05. Ang kanishang 0.05 is actually based from kanisha na requirement. It is estimated that the damping in the structure is in order of 5% of the critical damping. So 5% of the critical damping. So mo na siya. Okay? So the third one now is we can approximate our logarithmic decrement sa atong gi-solve ganihan, no? So ln of u0 and u1, so this one is the bigger amplitude, this is the smaller amplitude, or the bigger displacement divided by smaller displacement is equals to the, the 2 pi epsilon, no? So kaning 2 pi epsilon, ganihan, we have derived it earlier. So if we're going to solve this 2 pi times epsilon, its value is around 0.314. Okay? So, the ratio between two amplitudes now is therefore UO divided by U1 is 1.17, no? Okay. Ang kaning 1.17, okay, wait sa. Kaning 1.17 atong gikuhaan ni niya is okay. Balik ta diri. Let's see. Okay, the number of cycles that we can record the amplitude to be reduced from initial value of this one to this one, no? So, yeah, okay. So, okay, sige, I'll clear this up later. Asa ko nakuha ani niya. Okay, so kani 1.37 or maybe this is just a typo. So, I forgot na. It's been a while. Sige, ako lang i-clear up later on. So, pero sa pagkaroon kay we have what you call a two consecutive na amplitudes, no? U, O, and U1, which is this ratio. So, what we do now is to get the ratio between the first amplitude and the amplitude K, we need to determine the cycles, no? How many cycles does it need to take, no, sa ato ang ratio na initial value from 0.1 inches to 0.01 inches, no? So pila daw ka cycles ang require para mahitabo ang iyang displacement from magsugod from 0.1 mahitabo siya 0.01. So what we do is first is we need to have a relationship between the amplitudes, diba? So what we had discussed earlier, the ratio between the amplitudes is actually is measured between two successive peaks, no? So first two successive peaks is U0 and U1, and then U1 and U2, and so on and so forth, no, until na pinaka last na amplitude that is measurable. Okay? So what will happen is, if we are going to do the math, ang kani U1, U2, U3, mag-cancel na siya. So kani daw siya, kani na equation is just equals to, no, U0 and UK. Okay? So, if mo na ang iyang relationship, no, if you're going to get the natural logarithm of this equation, so it is actually the natural logarithm, the logarithmic decrement, and then ang kanino siya, if you get the natural logarithm, is still the logarithmic decrement, and so on and so forth, which is equals to, if you add them all up, ang mahitabo ano niya, the logarithmic decrement times its stiffness. Reason being, no, ang reason being ngano nagka-multiply na ta sa stiffness is because our system is decaying over time, and that decaying over time is dependent upon, of course, our stiffness as well. So mo na ato ang reason na naatay K here, no? So if you add this all up, no, natay K, no, pila ka number of delta atong gi-add times your logarithmic decrement. So ang kaning K, which is what we have solved here, no, kaning logarithmic decrement, kani siya. So mo na itong i-equate, no? So therefore we can solve for K. Ang K therefore is, or which is the number of cycles, no, the number of cycles is equals to the logarithmic of the value 10 divided by 0.318. So this is our logarithmic decrement, the value, and then kanisha, this is not delta, this should be K. So we are solving for the K value. Okay, so solving for the K value is equals to ln of 10. So ang asa gikuha ang L of 10 kanisha atong simplify, and then divided by 0.314, we can get approximately 8 cycles. So meaning ana niya, it takes around 8 cycles for your displacement mo reduce from 0.1 inches to 0.01 inches. Okay? So mo to ang meaning ana niya, and then the damp frequency now can be solved now because we already solved for our omega, no? We have solved for our epsilon, right? Nakasolve na to siya ganiha, and then we need if we're going to substitute our values, no, we can get this one, 31.02 radians per second, which is our damp frequency of the system. So a reason why we want to get the damp frequency of the system is we need to solve for the natural period. Kani siya. Ang reason why we need to solve for the natural period, no, it's because we want to know pila man ka seconds, how many seconds does it take to for these 8 periods to pass, no? So in this case, no, it is 1.62 seconds. So very short na kayo. So after 1 second, so ang interpretation ng Aliyah, it vibrates 8 times in 1.62 seconds, or it vibrates 8 times in 2 seconds, more or less, no? So pas-pas kay siya, no? So in summary sa kanina problem, no, we have solved for the undamped angular frequency, the absolute damping coefficient. The third one is the logarithmic decrement, no, which is nakasolve ta earlier, which is the katong ato ang ratios of U0 and U1, U1 and U2, and so on and so forth. And then the number of cycles does it take to require. Ang reason why we have this one as a problem, it's because if we are going to do the experiment, no, we need to know unsa man gid ang behavior or pila man ka seconds ang mapas when we do the experiment, no? So if we can calculate pila ka seconds niya, so we can verify it sa experimental setup na to. Okay? So and also another important factor, if we know how many seconds it takes, no, to vibrate or to oscillate ang system, we can now determine pila ang ato ang reading rate. Ang kaning si reading rate is what you call the frequency of reading, or hertz, no? So sa accelerometer man good, if you're going to use an accelerometer, we need to read, no, let's say for example let's say 100 recordings per second. This ensures that dili ta ka miss out sa mga peaks. Okay? Kaya lisod man jud kaayo kung 10 recordings lang per second, meaning ano niya, there are in this sa kanina particular problem, nahitabo na naka-vibrate na siya 6 times. So, if naka-vibrate na siya 6 times, most likely wala ka capture ang ihang real behavior of the structure, ang real niya na frequency. So, if solving for the number of seconds, no, pila ka cycles does it take, or pila ka number of cycles does it take para sa pila ka seconds na labaw, we can ensure that we have what you call we need to calibrate our sensor karon, our accelerometer. So that is why, or mo siya ang importance of number 4. Okay? So, mo to siya, no? Ang kanina problem, I will put more on sa to. Akong notes kay naa sa pikas na sa to, na notebook. So, I'll put this more and clean this up, no? So, ngano siya na 0.314, I think naka-explain siya, pero kani siya asa ko nakakuha og 1.37. I think this is a typo siguro. So I'll get back to you on this one, but ang important na answer is actually this one. If nakabantay mo sa atong course of our lecture, wala gid ta nakagamit og 1.37. So I would suggest wala gid na siya. Okay? Basin mo ni ining pamutana. Okay? So going back, ngano nakakuha tag kanina relationship, it's because moto ang nag-measure man ta sa number of peaks, no? So how many number of cycles does it take, no? So the ratio between the first peak and the second peak is actually the logarithmic decrement. The second peak and the third peak is another logarithmic decrement, and so on and so forth. So if we add all of these together, it becomes number k, no? So meaning ano sa K is number of logarithmic decrements that that has passed no sa kanina system. So we try to solve for the K value. Okay? So hopefully that clears things up sa kanina example, but before we move on, nababatay unsa to? Yeah, there kanisa. So e to the 0.134 is 1.37. So ako na i-clear up later on. But yes. So mo to siya no. So we have our example. So second example, second to the last, and do we have questions and clarifications? Oops. Questions and clarifications before we move to the last example. So one last example na ta. Wala ka? Okay ka? Okay, so wala ka siya, no? So, ano ako na-close? Okay, there. Okay, so we'll go now to the last example for tonight, no? So, ang kanisya kay nanatay what you call a beam system, no? So, natay beam system, and then what we need to know is we need to get its equivalent na system, no? Na easier system. So, ako na i-read first, and then we will understand why, no? Okay, so so natin machine weighing 1,000 pounds is mounted through springs, no? So mali ang springs, and then it has a total stiffness of the spring is equals to 2,000 pounds per inch, and then this machine that is being supported by the spring is actually being supported by a simply supported beam, no? So simply supported beam.
Yes.
So what we need to know now is we need to determine using the analytical model to get the equivalent mass, no? The equivalent stiffness and the equivalent damping for the system, and we assume that it has a 10% of the critical damping. And of course, para sa yan atong kinabuhi, we just neglect the mass of the beam, no? So this is our free body diagram. Naatay simply supported beam, naatay weight, no? Block of weight which is around 10,000 pounds. So ang iyang oscillation is going this direction, no? So more siya mahulog na ang kanina weight is maana siya up and down iyang response, no? And then we have the stiffness of the beam, no, which is EI, no? EI over L, or EI is 10 times 10 to the 7 times pound per inches squared, and we have the length of the beam is around 40 inches. So the load is actually applied at the middle of the beam. So what we need to do now is we want to equate this system, no, into a simpler system that na kay effective K, the spring effective K, and then the effective damping constant and the effective mass. So ang effective mass is actually based on the weight, no, weight of our system and the beam, no. So mo to atong buhaton. So first is if we want to get the effective stiffness K. So ang effective stiffness K, if mo go back gyapon atong lecture, no, so mobalik gyapon ta sa kato ato theory of elasticity. So force is equals to spring constant times the deflection. Okay? So if you want to get the K, imo kinahanglan is the K is equals to force divided by this displacement. And the displacement is usually at the point of maximum deflection, no? Or not necessarily maximum deflection, but the deflection of interest, no? But usually it is the maximum deflection. Okay? So, ang maximum deflection of a simply supported beam, kung usargit na point load, the maximum deflection based on our study in theory of structures, no, using the superposition method, it's PL cubed over 48 EI, right?
Yes.
So hence, if we want to get the stiffness of our beam, no, what we do is we divide our deflection, divide it by L cube, no, with the so P divided by the delta. Okay? So what will happen now is natin 48 EI over L cube kay mahitabuan ni siya kung P over delta kani siya mo cancel out, right? Then mo invert siyang duha ka buok. Okay? Mo siya mo inverse. So ang EI is given, which is 10 to the 7, right? 10 to the 7 pound per inches squared cube. And then ang length set is given, which is 40 inches. So substituting those values, we get 7,500 pound per inch. Okay, so ang karon, no, if we want to get the equivalent stiffness of our beam, we need to imagine, is this stiff, if this system, is it in parallel or in series, no?
Series.
So ang kani daw siya na system, we can imagine it something like this, no? Kung nakoy support, kani siya, so kani ang beam, then nakoy spring, and then siya nakay another spring, and then nasa another spring, and then nakay kana, no? So kani siya na spring is K beam over 2, K of beam over 2, and then this one is K of spring sa atong system. So if we are going to imagine it like this, then our system, or the springs, no, is actually in series. So going back to our previous lecture, kung in series ganit siya, we have to use this equation. Katong 1 over KE is equals to 1 over K plus 1 over KB, no? So basi nakalimot na mo, akong i-review lang. So if you want to get the equivalent stiffness of our system now, no, it is we treat the springs as a series, no, and then we compute it, and we compute the equivalent stiffness. So if natin equivalent stiffness, we also have the equivalent mass. So again, equivalent mass, because we are neglecting the mass of the beam, ang 1,000 pounds ra atong gamiton. Okay? So ang last one is the critical damping, no? So the critical damping is base gyapon, no? So 2 times ang atong gamiton karon is the equivalent stiffness and equivalent mass, right? So equivalent stiffness and equivalent mass is equals to 127.92, no? So if we do the calculations, so from there, wala na. So if we want to get the equivalent na damping, we will need to use the relationship epsilon is equals to the equivalent damping divided by the critical damping, no? So mo na siya. So in short, if we want to get the equivalent damping constant, we just multiply the damping ratio times the critical damping. So which is, damping ratio was given to be 10% times our critical damping, which is 127.92, and that gives us the answer of 100 na lang, 12.79, and this is your answer. Okay? So ang reason why we need to convert our beam into an equivalent system, it's because if natin equivalent system, it's easier to solve our equations of motion, no? Because our equations of motion is mx double dot plus cx dot plus kx is equals to some forcing function, which is we're going to discuss after midterms, no? So mas easier ni siya kani siya. So if we don't do this, then what will happen is we will solve the beam as an individual na individual but continuous na system, which is what you call a multiple degrees of freedom na system. Kani siya, it madugo siya because it's a higher form of math. We require linear algebra and eigenvalues and eigenvectors, no? So if you don't want to deal with those chuchu, kani atong gamiton. So no matter how difficult the system is, we can actually we can simplify the system using what we have learned in the previous chapter, katong springs in parallel and springs in series, no, the concept. Okay? So moto siya, no? This is the last example, and then of course we have the problem sets, no? So kani problem sets again, we'll be submitting this one to next week Saturday lang. So you have 1 week to do it, no? Kung group ba mo or something. And what I have said earlier in the lecture, na if you did not solve for problem set 1 and problem set 2, dili gid mo ka-answer sa problem set sa chapter 3. Okay? So mo to siya. So before we end the lecture, nabatay question and clarification, no? Asa to ko. There we go. So do we have any also to? How do we proceed with the problem set 2.1? So since okay. Sorry. So problem set 2.1, since the problem set 1 point doesn't have any given values, okay, mostly concept. Yeah, actually, it's concepts and formulas kid. So the answer is actually in terms of M, K, and C, no? Or what I see, M and K, so. So if we go back to our Kanisha, okay, determine the natural period of the system. Assume that the beam and assume that the beam and spring is supporting the weight W is massless, no? So the answer is actually in terms of W and in terms of tawag ani, in terms of K, no? Wala gid siya value. Inana gid siya. This is actually designed that way. So you have to, so kamo karon kay you have to force yourself to solve in terms of W's and K, no? So ang problem set number 1.1 is actually ang iyang answer niya is in terms of variables, no? And then the only difference karon is naki-cantilever beam, but that cantilever beam is being supported by two springs, no? So how if mo na ang iyang ang iyang problem, how do you solve this one? But ang kanina problem 1.1 is very 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 similar sa kanina problem. Asa to? Where is it? This one, no? Pero kanisa, nara siya value. Kanina siya value. And then yung spring kay na siya diri. Ang nahitabo karon kay ang yung spring kay nasa kay na kay mastery, and then nasa kay spring here and then another spring here, no? And then surface and then surface. So moto ang more siya kanang tawag ani more siya kana division, no, sa first na problem. So hopefully that answers your question kay dili ka solve, actually makasolve gid na siya, but it is in terms of M and K's, no, in variables. Okay, so hopefully that answers your question. So any other questions before we end? So kanisa na question, this should have been asked sa atong chapter 1 naghimo ta sa assignment, no? So this goes to show na wala gid nag-solve ang uban. No? Okay, wala man nag-ask. So any other question? So we don't have problem set 1, right? Yes, actually ang problem set, okay, balik na ha. Katong problem set 1 is if you understand 1, problem set 1, ang problem set 1 is sa chapter 2, which is kanisya, the problem set. So problem set 1.1, 1.2. So this is the first problem set. The second problem set is kanisya kato akong gi-submit karon, which is kani, no? So tulo na lang ka problem. Okay? So from 6 nahimo kog tulo para masayon. So yes, moto siya. Okay, any other question? Okay na ta? Well, there is no other question, no? So ako i-extend kay sige mo man ang hangyo period nato sa atong semester, no? Sa kanina course di ay sorry. So you have the whole semester to do the assignments, no? Sorry, to increase your grade, no? Pero kung naka-final exam na ta, wala na tay hangyo-hangyo because the hangyo period is within the semester. So if you don't do the assignment, well, it's your decision. And then I'm telling you now that now the exam is based on the assignments as well, the problem sets, no? It's very similar but not exactly the same. Kaya basin ang buhaton nato is mag-memorize na lang ta. So which is a no. We have to analyze our structure, no? So again, the purpose of the problem sets is for you to practice. Okay? So anybody else na tay question and clarification? If wala gyud gani, then we can actually end the session karon. So na pa or wala na? Wala na, no? So usara ka buok na reply, no? Done. So wala space sa utok. 1 hour, 1.5 hour ganito nag-discuss. Wala ganito 3 hours, no? So I would suggest na again, no, if nag-isot mo sa chapter 3, go back to chapter 2, the problem sets. If you solve the problem sets, then mas easier to understand ang chapter 3. Then if you understand chapter 3, then you can actually solve the problem set. So sa kamo, ang advantage gani sa ato karon kay natay Google Space, no? So if na may question sa mga problem sets, you can actually ask sa Google Space, no? No? Sa Google Space, dili ko ma-reply sa if na question mo reply sa direct message sa kuha, mo answer ko sa kanang sa Google Space na to. So you post the question sa Google Space and you have to be proactive pag initiative mo. Kung namoy question pamunta na dayon, if dili ka to pag imong classmate, then you can ask me and how to solve the problem sets, no? Pwede ko mahatag tanan solution. I just mohatag ako hints unsaon. Because again, the problem sets is for you to unsa to? It's for you for your practice kay I already solved several examples naman, no? So those examples is so those problem sets is actually a spin ra gamay ra na spin sa examples akong gihatag. Okay? So since wala naman, no, so let's end this session to now. So dili kay sa lisod, no? So pero ang kanisa na topic, ang chapter 2 and chapter 3 is mo na ato ang so to coverage sa midterms, no? So next week, I will not be doing any lecture. Dili na lecture. We will be solving you will be solving problem sets na naara ko sa unsa to sa school, no? Just to cater. Pero pwede ra jud na we don't need to meet next week if you can solve it by at home, no? So muli na lang mo you solve the problem sets there. Okay? So if not a clarification, we'll just do it via online or you just chat and then mag-meet ta online unsaon na siya. Okay? So to save time and of course pliti sa ninyo to go into schools para makasave tag time. So again, no, next week we will just meet kung kinahanglan ta kinahanglan og help sa atong problem sets. So your goal is to solve, no? To solve all the problem sets, problem set 1, which is sa chapter 2, and thus the new problem set, which is chapter 3. More gid atong buhaton. So you are given the time to do that para makasubmit ta sa exit work, and then those those problem set is also your notes para sa atong midterms. Okay? So if wala tay other questions, well, we are free to go na. No? So, mato siya, you can do whatever you want na afterwards, then, but I would suggest you solve the problem sets. Okay? So, that is for tonight, no? Sige. Okay, I have to take my medicine asad.
Thank you, sir.